All right, good afternoon and welcome to ECE 164. Today we're going to talk about operational transconductance amplifiers, or OTAs for short. So before we get into exactly how to build these types of amplifiers, I want to talk a little bit about what they are specifically. And in order to do that, we're going to start by describing a little more familiar amplifier, the operational amplifier. So an operational amplifier has two inputs. We would call this differential inputs, and it has a single-ended output that's referenced to ground. Implementing such an amplifier would look something like this. We have a differential pair here, a tail current source, a current reference that's set up with a current mirror, and then we have a load on this. In this case, it's an active load. We'll describe a little bit how to analyze this type of structure today. You can think of this in some sense like a current mirror here. The important difference, though, for an operational amplifier is that it has low output impedance. Okay, and if you think about uses of an operational amplifier, they can drive resistive loads, they can drive capacitive loads, and so the ability to buffer the gain stage from the output load is very important. Otherwise, we would load down this node and potentially not make any gain with this amplifier. On the other hand, operational transconductance amplifiers, OTA, they structurally look very similar. In fact, they're identical to what we've shown here, with one exception, and that's that the output is high impedance. Okay, so there's no output driver that would be used to drive a resistive load. This is often denoted in the schematic by having this abbreviated version of the triangle, trying to indicate that there is no output stage present on this particular amplifier. So the very key difference, low impedance for an op-amp, high impedance for an OTA. There are a few other differences that I can quickly iterate on in terms of op-amps and OTAs. Op-amps are meant to be more general purpose. That is that we're going to design one op-amp and we will use it for various different applications, maybe with different feedback networks around it. It really is kind of designed in the sense that it doesn't know what it's going to drive, and so it assumes kind of worst case scenario. These are better described as voltage-controlled voltage sources because of their low output impedance. They take a differential voltage at the input, and they have a low output impedance that they then apply that output. This means that they can drive both resistive and capacitive loads. And as I showed earlier, it's essentially just an operational transconductance amplifier and a buffer. And so, reasonably, you could be asking yourself, well, what's the big deal? Why do I care about this buffer? Most of the time, this buffer is going to cause a pretty significant increase in the power consumption. And it can also be very complicated in terms of the design. As we start to add more stages to this amplifier, like we talked about in the multi-stage amplifier lecture, you can pick up a lot of poles and zeros. And so if we're open loop, these poles and zeros that you're adding may not be such a big deal, but once we put them in feedback, these poles and these additional zeros can be quite cumbersome to compensate the amplifier. That is, to achieve stable operation. OTAs, on the other hand, almost all amplifiers that you're going to find on chip are OTAs. These are better represented by voltage-controlled current sources due to their high output impedance. We typically don't use them to drive resistive loads on chip, as you'll see later on this lecture and in a few lectures as well. We're mostly going to have capacitive networks. These capacitive networks can be in various different forms. They can be in switched capacitor to mimic resistors, but fundamentally they are not resistive in nature. They are capacitive. All right, so how might we actually build one of these OTAs? Well, very much like on the previous slide, we have a tail current source that is being biased by a current mirror and a reference current. We have our differential pair, and then here I'm showing a load device on one side of the output. Okay, so the previous slide showed the ability to mirror this current back over to this side. If we just wanted a single-ended output, we could also have just taking the output from one side. Okay. Importantly, remember that this differential pair is simply steering the current or shuttling the I-tail between these two sides. And so if we're not taking the output from this side, i.e. we're only using half of the differential output, it doesn't really matter if this is loaded or not loaded. And so here I'm showing you for simplicity that it's not loaded and connected directly to VDD. If I wanted to actually put this into an amplifier, I would have a capacitive input and a capacitive output, and this way the amplifier only sees a capacitive network where the gain of this is CS divided by CF. If you want to analyze this, we would do very much like we talked about before, where we would treat this as our differential amplifier, and in the differential mode, we're essentially going to have a virtual short here, okay? Or we could treat this as a multi-stage amplifier, as we did in lecture 8, I believe, or maybe 9 now. And what we did was we looked into this node and found the impedance, okay? And so that's what I'm showing here, is where we have this common source amplifier. We see it R0 looking down, and looking over into this other node here, we see 1 over GM, okay? And so R0 in parallel with 1 over GM is just approximately 1 over GM, okay? And so the network that I showed on the previous slide, we would abstract away this entire amplifier as having some transconductance, some GM, where in this case the GM is simply, capital GM that we're using for a compound transconductance is going to be equal to GM divided by 1 plus GM RS, where RS is this source degeneration resistor, which happens to be 1 over GM, which gives us our compound transconductance of GM divided by 2. Same thing with the output impedance. The output impedance, when we see looking back into this node, looking up, we're going to see ROP. And looking down, we're going to see R0 times 1 plus GM RS, where RS is the impedance that we see looking down this node, okay? And so that's how we end up with approximately this expression for the output impedance, 2R0, 2R0N in parallel with ROP. Okay. The capacitance that we're going to see looking in is CGS divided by 2, again for the same reason of this 1 plus GMRS. We'll talk about this next time. This is a form of feedback, and so what it's doing is it's changing our port impedances. It changed our output impedance by 1 plus GMRS, where 1 plus GMRS is a factor of 2. It changed our transconductance, and it also decreased our capacitance. Okay. And so what this allows us to do now is we can take this model of our amplifier as just a GM, an R0, as well as the output capacitance, and we can put this into this kind of structure where I have the two capacitors, and we could solve for the closed loop gain, the open loop gain, as well as look at the stability of this particular amplifier. We're going to spend a lot of time next lecture talking about feedback in particular. The focus that I want to get us honed in on this week is to understand this part. That is, in order to have very good closed loop amplifiers, we need a lot of open loop gain. Okay, and so how do we make structures that have lots of open loop gain that we can then use feedback in order to set the gain by the ratio of the passive devices? All right, so in terms of the output stages of amplifiers or op amps, Conventionally, I would say that we're most used to single-ended output. That is that we have one output and that output is relative to ground. With integrated circuit amplifiers, you're going to find that more often than not, we're going to have what's called fully differential outputs. Fully differential outputs means that we're not taking the output relative to ground, we're taking the output relative to another signal. So the same way that we have two inputs to an amplifier, we can also have two outputs to an amplifier. This has a lot of benefits in terms of its ability to reject things like supply noise or coupling. In addition, one of the biggest benefits for integrated circuit amplifiers is that it has twice the swing. So this signal can swing up, this signal can swing down, and instead of only swinging V volts up and having this node be relative to ground, it's V volts up and V volts down, so that's 2V. And so we get additional swing with using these types of structure. A reasonable question to ask is, well, why don't all op amps do this? It turns out that when I do this, I also need to double my feedback network. And so if I was doing a capacitive feedback network, that means twice as many capacitors around this amplifier. Which for an integrated circuit is definitely worth it to add these additional components for the benefit that we get. But for a PCB level or an op amp, it would require doubling the feedback network for everything. And so it's typically not used. There are some exceptions with things like analog to digital converter drivers is a good example. In addition to this, it requires a circuit that's called common mode feedback. The common mode feedback circuit essentially sets the DC output voltage of these two output signals. So very much like we have a common mode voltage to the input, the amplifier is amplifying the differential mode, but we need another circuit to come in here and set the common mode of the output. I'll talk very briefly about this today, and we'll spend a discussion section later on going into depth about common mode feedback. In terms of output stages, there's many ways of doing this. The simplest, I would say, is what's called Class A. Class A amplifiers or output stages, they can only source or sink currents that are the quiescent bias point. And so the most straightforward example of this is something that we've kind of been using, that if I have a current source, and this is going into, let's just say, an NMOS as my amplifier, the most current that I could pull out of this amplifier into my load would simply be I. So I'm limited in the amounts of current that can come out of this by the amounts of current that I can source. Okay, so this is what's known as Class A. You could also think of flipping this entire structure upside down, and again, you would find that the maximum current that I could sink would be this bias current. This is in contrast to Class AB output stages. Class AB output stages allow you to have output currents that go above this quiescent current, and I'll call this IQ. They typically require a little bit more biasing and have some other trade-offs in terms of their distortion and swing capabilities relative to Class A. So Class AB are typically what you would find in, for example, a rail-to-rail amplifier, whereas a Class A is very rarely going to be rail-to-rail. All right, so very quickly to talk a little bit more about the idea or the notion of single-ended versus differential OTAs. This is, as I showed you earlier, an example of a single-ended OTA. It is rather easy to bias, rather easy to understand. It's very good for learning the fundamentals. Okay, and so we're going to spend several slides analyzing and understanding exactly what's happening in this amplifier structure today. So this is going to be covered extensively in 164. Fully differential amplifiers, as I've said a couple of times now, these are really the way that amplifiers are implemented in integrated circuits. You will very rarely find amplifiers that are single-ended for many of the downsides that they have. You will almost always find amplifiers implemented as fully differential. They are a little bit more difficult to bias, in the sense that they have multiple stages here to bias the current mirrors. We have to match these two currents. Okay, for example, if this had 100 microamps, you need to make sure that 100 microamps is evenly divided between these two branches. So each of these should sink 50 microamps or source 50 microamps rather. And oftentimes what you're going to find is that there's a little bit of mismatch. So we talked about process variation in a previous lecture and showed that even if I make two transistors nominally right next to each other, based on their area, there's going to be some variation that's going to exist between these two transistors. It's not such a big deal for this differential pair. It would simply yield an input referred offset. It's a little bit bigger deal here in the sense that if these two currents don't match up, I could end up with a case where there was maybe 51 microamps flowing through this device, and the tail could nominally only sink 100 microamps. And so I have an additional 2 microamps that we're trying to force into this tail. This is where the notion of the common mode feedback circuit comes into play. It measures the output common mode of this amplifier, and it feeds back a signal, typically to the tail, in order to adjust this. And so typically what you'll do is you'll put something like 50 to 60% of the tail current in this device and allow the common mode feedback network to come back in and supply the additional 30 to 40% through the secondary path. As I said, this is a little bit more difficult to bias. It will be covered extensively in 264A. All right, so let's analyze this circuit. And what I want to do here is I'm going to go through kind of the entire analysis for both this structure as well as the fully differential structure. We'll look at some of the differences between them. And then I'm going to move on and talk about more advanced structures, but I won't go through the same type of rigorous KVL, KCL analysis that we'll do here. The idea is that you should be able to carry forward this type of analysis to those amplifiers. All right, so let's start off with a couple of things. One, we're going to assume that all of the transistors are operating in saturation. MNB and MP1 are diode connected. All of the other devices, we intend for them to be in saturation. These two are current mirrors. This is a current mirror, and this is our differential pair. So the intent of the designer here is that all of the transistors are in saturation. MP1 and MP2, these are the same size, meaning that they have the same W over L. MN1 and MN2 also have the same W over L. And MT and MNB are ratiometric, where K1 is the ratio of sizing between them. Okay, so this is a way that we could scale the current from I1, make it K times larger in the tail current here. All right, so we're going to go through and let's start first. When we're analyzing circuits, we'll always start with the DC biasing. And so we're going to start to calculate what the DC biasing for all of the transistors in the circuit are. So the input common mode, this is going to be VIP plus VIM divided by 2. And we know that the current that's flowing through this transistor here is I tail. Okay? And I tail is going to be K1 times I1. Okay? And so what this lets me do is I can calculate the overdrive voltage for starting with this transistor. Okay? This transistor, the overdrive voltage is going to be the square root of 2I1 divided by Kn W over L, which is going to be equal to the overdrive voltage of the threshold of the tail transistor, this device, where this device is going to have K times the current, but it's also going to be K times wider. Okay, and so these two are going to be exactly the same overdrive voltage by virtue that we're copying the same current density through the transistors. Next, we can calculate the overdrive voltage for the input differential pair. And so recall here that we have a current of I1 times K flowing through this device. And so we have half of that flowing through each of these sides of the differential pair. We're taking away the differential mode voltage whenever we're doing DC biasing. Okay? And so we get that the overdrive voltage for each of these devices is equal to square root of I1 times K divided by Kn W over L. The exact same analysis is true of the PMOS devices here. I tail over 2 is flowing through this half. I tail over 2 is flowing through this half. And so these two transistors have the same overdrive voltage and as well as the same current, which we can calculate using this. All right, now we can calculate all of the different node voltages that we have in the circuit. V and B, this node right here, is simply equal to VOV NB, the overdrive voltage of this transistor, plus VTN. Vx is this node here. This is equal to VDD minus VOV P12 minus the absolute voltage of VTP, the absolute value of VTP. The tail transistor, or the tail node here, this is equal to the input common mode, VICM, minus the overdrive voltage minus VTN. Okay? So remember that as the input common mode changes, this tail node shifts right along with it. So it copies the input common mode. It's just level shifted by VOV minus VTN. Okay. All right, and then the last one, which I'll prove to you a little bit later, but we can get a sense of it right now, is that the output voltage is approximately going to be equal to Vx. Okay? This one is a little bit trickier and not always true, but if you think about it in the following way, the current that I have through each of these sides is equal. They both share the same gate and they share the same drain. Okay? And so this node voltage is going to be approximately equal to this replica path over here. I say approximately because it's not quite true. It really is a little bit dependent on the output impedance that we have. So we have a GM and we have an R0. We have, if I have, let me explain it this way. It's essentially like I have two current sources and they're connected together, and we ask what this internal node voltage is. So in an ideal sense, if these are perfect current sources with no output impedance, this can be any voltage. Okay. Once I start to add some finite output impedance with each of these sources, it turns out that this voltage now depends heavily on the output impedance. Okay, and so this is where we have to solve the expression, including the lambda terms, in order to figure out what this DC node voltage is. As a good first proxy, we can use the other node voltage. So we can say that V out is going to be approximately equal to Vx. All right, so now let's look at the common mode. So in particular, the common mode, what's happening at DC voltages here. So what I want to understand is what is the minimum and the maximum range that the common mode voltage can be applied to this circuit. And so when we're talking about the minimum common mode voltage, I want to know if I was to take both of these two inputs, VIP, VIM, tie them together, how low can I take this in terms of voltage and still keep all of these transistors in saturation? Okay? And so the best way to approach this is to think about what is the minimum voltage that I need to keep MT1 in saturation. That's 1 VOV. And then I also need a VOV plus a VT in order to keep the input pair in saturation. And so that's where I get VOV tail plus VOV N12 and VO plus VTN. On the other extreme, we should ask ourselves, how high can I take the input common mode before one of these transistors comes out of saturation? Okay. And so I can follow this path that I've highlighted here in blue and say that the input common mode max is equal to VDD minus what I need to keep this transistor in saturation, which is just 1 VOV. Okay. And then I come down this node. In order to cross this, I need 1 VOVN. And then I go back up, and that costs me a VOVN plus VT. As you can see, the two VOVNs cancel out. And so my input common mode maximum is VDD minus VOVP plus VTN. Okay? And so if we're looking at this particular structure, you would say that an NMOS differential pair is very good at picking up high input voltages. That is, it has a high common mode input range. However, it's not very good at picking up low input voltages. We're limited here by VOV plus a VOV plus another VT. So 2 VOV plus VT. And if you kind of think about typical numbers, just to frame our reference here, if this was 150 millivolts for each of these two, and this was 500 millivolts, this would say that we could sense as low as 800 millivolts. On the high side, we have 1.8 volts, minus 150 millivolts, and then plus 500. This actually puts us at greater than VDD. So 1.8 volts minus 150 millivolts, and then we're going to add 500 millivolts on top of that. This says that I can sense what's called above the rail. Where rail is typically a slang kind of word in integrated circuit design for the supply voltage. So when we're saying above the rail, that means above the supply voltage of VDD. All right, so my minimum and my maximum voltage, we just talked about those. The output voltage also has a range. And if we look at the output and we apply the same kind of analysis that I just did, how high can this go? The maximum is going to be limited by keeping MP2 in saturation. That's going to require 1 VOV. On the low side, we can take this down to the tail node here plus 1 VOV. Okay, and so remember that the tail depends on this input common mode voltage. All right, so now if we start to move on to the small signal biasing or the small signal analysis of this, we can write out all of the small signal parameters. Starting with this device right here, we can write that the output impedance is equal to 1 over lambda, where lambda is going to be a function of the length times the current that we see through this. And I'm referring this all back to this current I1 based on the ratioing of these currents. We can do the same thing for the PMOS devices to get the output impedance. It's exactly the same expression, and we have the same current here. The tail node is going to have some output impedance here as well. And then we have the two transconductances, GMN and GMP, which are given by these two expressions shown here. All right, so now we need to actually spend a little bit of time talking about this particular structure and what's going on here. And so what I've done is I've drawn out the small signal model of this. On this side, we have ROP2 and we have GMP2. On this side, we have ROP1 and GMP1. And the part that I want to kind of point out is that this device here is diode connected. Okay, and so this diode connected device, when we're looking up into the various different parts of this, what I want to know is what is the impedance here and what is the impedance seen here. Okay, and so we can simplify this diode connected device as having an impedance of 1 over GM. And when I try to calculate the output impedance on the other side, I'm going to see ROP1. Okay. So this is my simplified small signal structure of this device. Okay, so I have a resistance down here that's due to the output impedance of the tail transistor. I have the small signal model for my input differential pair, GMN1 and GMN2. And then the load, I have slightly asymmetric, not slightly, quite asymmetric load. One side I have 1 over GM, and the other side I'm going to have R naught. Okay. Importantly, what this means is that when we don't have a fully symmetric circuit, we can't use techniques like half circuit analysis. Okay, and so we're going to have to resort to doing KCL and KVL in order to solve this circuit. All right, so with that said, let's dig in, and we're going to start analyzing this. I will start with the differential mode, and then we'll do the common mode next. Okay. All right, so starting at VG1, that's the node right here. I have current that's flowing through this top resistor GMP1. I have current that's flowing through GMN1, and I have current that's flowing through RON1. Again, my notion on all KCL is that I'm going to say that the current is leaving the node. So I always have it equal to 0. At the output node on the other side, I'm going to have current that flows up into this transconductor GMP2. I'm going to have current that flows out of GMN2, and then current that's going to flow into ROP2 as well as RON2. Right here and here. And then at the tail node, I have current that's flowing through ROT, current that's flowing back up through RON1, RON2, and then negative current that's flowing into GMN1 and GMN2. Okay. Notice that here we're analyzing the differential mode, and so I've applied half of the differential mode signal to this side, VIP, and minus 1/2 of the differential mode signal, VD, to the minus side, VIM here. All right, so here we've set up all of the expressions, and now we just need to solve for the small signal voltage gain, namely, what is Vout divided by VD? All right, so I'm going to rearrange this a little bit and simplify things. First, just grouping the terms in terms of their voltages. You know, I could rewrite those first 3 equations. I do see something here that I want to point out, and we've said it many times, but it's not always as obvious when it's written out like this. When I have a term here that's GMP plus 1 over R naught, it's the equivalent of me drawing a circuit where it's diode connected. And so every time that we've seen 1 over GM in parallel with R naught, we've always said that we can extract this away as just being GMP. Okay, and so we're going to apply that. You'll see that many times. Oops, not that one. Many times in this expression, that this type of 1 over GM is going to be in parallel with R naught. So we're going to drop all of those terms, and we can simplify the expression to now look like this. So we have 3 expressions, we have 3 unknowns, so we have a system of equations that we can solve. There is one other point that I'd like to simplify here, and that's that in a differential circuit, we know that this tail node here is a virtual ground. Okay, and so what we are going to do when I make this simplification is, with my knowledge of how this differential circuit works, I'm going to say that no current flows through this device. Okay, and the reason is pretty simple, that in a differential circuit, I can have a differential current here, I, but I have a differential current that flows in the opposite direction on the other side. That is, everything is symmetric in how the currents flow. Okay, and so what that means is that if I have I coming out of this node and I entering this node, that this node current has to be 0. Okay, and so what we're doing is we're removing this ROT term here, and that's why we don't see ROT in any of our expressions down here. All right, so just rewriting my expressions here for convenience. Now I'm going to do a little bit of what I call sloppy math. Sloppy math is where I'm going to take this second expression and I'm going to subtract it from the first expression. Okay, and so what you'll see is that when you do this subtraction, you'll get an expression that looks something like this, where I have that the output voltage divided by R naught is equal to GM-N1 times VD. This V out divided by VD, this is my differential mode gain. And that's going to be equal to GM-N1 times ROP in parallel with RON2. Okay. I call this sloppy because if you do this subtraction before you drop the RO terms, you end up with that VT term that we just talked about. And so this, this math is not quite clean in that regard. However, it is still justified given that VT is much, much less than VO, and so there's really no reason to keep around this VT term. All right, we can also add up all of the expressions together in order to calculate VG1, and so I can calculate that VG1 is going to be equal to minus V out divided by 2 GM-P1 times ROP1, which I can rewrite as shown down here, relative to VD. And then I can simplify this by saying that the R naughts are roughly equivalent, and so I get a ratio of GMs here. Okay, and so this now lets me write all of the nodes in this expression, but the key expression that we derived from this analysis was the differential mode gain that we're showing right here. All right, so now we're going to repeat that same analysis, but we're going to do so for the common mode gain. Okay, and so the common mode gain means that rather than applying half of the differential mode signal to one side and half to the other side, we're going to apply the input common mode signal to both sides. So same KCL expressions. We're going to have current that flows through this GM here. We're going to have current that flows through GMN here, as well as current that flows through RON. The key difference and the only difference between the expression that I showed before is that instead of VD over 2, this is now VIC. Okay, and so we're going to repeat the same expression at the output voltage, and we're going to repeat this at the tail node, and we're going to get these expressions. When I rearrange all of the terms to pull out VGs, VTs, and VOs, you'll see that we're left with this expression. I'm going to do the exact same thing of having 1 over GM in parallel with R naughts. And I'm going to be able to then write out the common mode gain. And so the common mode gain, AC, is equal to how much the output changes when I have input common mode signal. So VO divided by VIC in our expression. And if I look at this expression and subtracting it from this one, before we had kind of addition, we had a VD over 2 plus a VD over 2, so we ended up with a VD term. Here, these two terms cancel out. And so what that means is that we end up with this term on the right side being 0. Okay, and so what this says is that our common mode gain is equal to 0, and our common mode rejection circuit, or our common mode rejection for this circuit is infinite. Okay. If we don't drop the RO terms relative to GM, we can solve and get an expression where the common mode gain is equal to 1 divided by 2 GMP2 ROT, which gives us a common mode rejection ratio as shown right here. Okay. More often than not, the mismatch is really going to dictate the common mode rejection ratio, as well as this tail transistor. So this is why whenever we want good common mode rejection, we always try to increase the tail node output impedance as much as possible. Okay, because GMP2, it affects the differential path as well. ROT only affects the common mode path. Okay, so now you might be asking yourself, well, what about the frequency response of this circuit? It turns out that the poles and the zeros of a differential circuit are equal to the poles and the zeros of the half circuit. Okay, and so once we find the poles and the zeros of a half circuit, if it is symmetric, we know the poles and the zeros of a fully differential circuit. This particular circuit has a undesirable effect from this current mirroring at the output. It has what's known as a pole zero doublet. Okay. The easiest way to describe this is that if I was to look at the complex plane, is that I have a pole and I have a zero, and they're nearly at the same frequency. Okay. If they were exactly at the same frequency, we would end up with pole zero cancellation, which would be perfect. We would like that very much. However, the pole zero doublet refers to me having a pole and a zero that are very close in frequency, but not on top of each other. Okay, and so this can give rise to some very bad frequency response. It can have very slow settling in particular. It can also induce ringing in the output. Okay, and so the question is, why do I end up with this? Both of these circuits have very similar amounts of capacitance at the output nodes here. Okay. And so if we were to think about the impedance that they see, this capacitance sees a 1 over GM, and this capacitance sees an impedance of R naught. Okay, and so it's really this this asymmetry in the impedances that gives rise to this pole zero doublet. Okay, and you may be asking yourself, normally when I think of a zero, the zero comes from this capacitive path to the output, right? So classically in the common source amplifier, we've said several times that CGD gives rise to a 0. So signal coming in here, the conventional path is that the signal goes through the transistor, gets an inversion, gets turned into a current, and then turns back into a voltage through this resistor. And CGD allows the signal to quote unquote race ahead to the output with this alternative path. The same is true in this circuit, except we're doing it by design. We have a current mirror up here that is copying the current from this side over to the other side. Okay? This is what's giving us the 0. The 0 is coming from this nature of copying the current and feeding it to the other side. So just in the same way that the single-ended amplifier had an alternative path to the output, this circuit has an alternative path to the output as well. The main path would be through this transistor that's sitting down here. This is the common source amplifier. We would consider this the main path. We also have this secondary path on this side. However, it takes a different route to the output. That's where we get the 0 in this particular circuit. Okay, the pole occurs on this right side over here from the output that we see the capacitance from this transistor as well as P2 with the impedance that I have at that node, so the output impedance. Okay. This structure of having a diode connected load that's mirroring the current to the other side, it also results in what's called a systematic offset at the input. So a differential pair, if we have perfectly matched transistors for the differential pair. Recall that back in an earlier lecture, we said we like to refer all of the errors back to the input. And if it's perfectly differential and the transistors match, that is, they have the same W over L, we have no offset. In this particular case, since we have the asymmetry in the loads, even if all of the transistors match perfectly, what's going to happen is that we're going to have a current that is different on each side. And this current that's slightly different will result in what's called a systematic offset, referring back to the input. All right, so now if we look at a differential amplifier, you'll see here that I'm showing a fully differential amplifier. We're going to go through the same analysis that we did for the single-ended amplifier. However, it's quite a bit easier and much more straightforward given the symmetrical nature of this structure. The same setup as before. All of the transistors are operating at saturation. MP1 and MP2, the load devices, are the same size. K1 is going to be the ratio between MNB and MT1. And K2 is the ratio between these two devices. So we're simply allowing ourselves the ability to ratio the currents with K1 and K2. All right, so in terms of DC biasing, I'm going to write that the input common mode is equal to VIP plus VIM divided by 2, as well as the output common mode is equal to VOP plus VOM divided by 2. Okay. And so what this is simply saying is that VOP is going to be equal to VOM, which is what we're going to call VCM. All right, so calculating the overdrive voltages, again, for each of these transistors, starting with this diode connected device here. This device has I1 amount of current in it, and so its overdrive voltage is the square root of 2I1 divided by Kn W over L. This is going to be equal to the tail device as well, MT1, okay, where it has K times the current running through it, but it also is K times larger. For the load device, same thing. We're going to calculate this now based off of I2, since this is a current mirror structure that's copying the currents over here. And this allows us to do MPB as well as MP1 and MP2. Okay. Lastly, we have the input differential pair, where the total current that's flowing through this is going to be equal to half of I2 times K2. And so we get that the total current is 2I2 K2 divided by Kn times W over L. Now calculating each of these node voltages, VNB is equal to VOV plus VT. VPB, that's this voltage, is equal to VDD minus the overdrive voltage of MPB minus the absolute value of VTP. Lastly, the tail node here is going to be equal to VICM minus VOVN1 minus VTN. That is, that it's just a level shifted version of the input common mode voltage. Importantly, I'm not calculating VOM or VOP here for the same reason that I was describing earlier, that this really looks like two current sources. This one due to MP2, this one due to MN2, and if I have two perfect current sources, it doesn't matter what voltage is here, they're both going to pull I current through them, okay? And so it's really this common mode feedback circuit's job to adjust the current NMT2 in order to set both of these to this voltage, to VCM. Okay, so that's the entire point of the common mode feedback block, is that it's going to servo the outputs VOP and VOM, and it's going to set them equal to the desired common mode, which in this case is VCM. Okay. We'll talk a little bit about this particular structure, but in reality, it actually looks a lot like this differential amplifier shown here. Okay, so it's just going to measure the difference between these two voltages relative to the common mode voltage, and it's going to apply a voltage here that adjusts the amount of current that's flowing through this in order to move up or down these voltages. All right, so now if we look at the input common mode range, we're going to do exactly the same thing as we did before, starting with DC, the minimum common mode voltage range, that is how low I can take these two inputs. It's limited by keeping MT1 in saturation and MN1 in saturation. And so I have VOVT1 plus VOVN1 plus VTN. On the maximum side, when I try to raise up these two inputs, I need to keep one VOV for this transistor. I go down a VOV and then back up a VOV, and that cancels out these two, and so I'm left with the minimum input common mode voltage for the input is simply this, and for the output is VDD minus VOV plus VTN. Okay, so exactly the same expressions that we saw from the single-ended analysis earlier. In terms of the output common mode, we need to keep this device in saturation, and so that means that we need VT here, the tail node, plus 1 VOV, and the maximum that we can take it up is VDD minus 1 VOV to keep MP2 in saturation. Small signal parameters, exactly the same as before, with one exception, that when we're calculating the tail impedance looking down here now, we have two tail impedances. We have ROT1 and we also have ROT2 that's due to the common mode feedback circuit. And so I've written this out here where we're giving some amount of current to the common mode feedback that is the difference between these two currents. And so if you kind of work out the KCL, you'll see that this current should be 2I2 K2 minus I1 K1. And then lastly, we're calculating the transconductance of the input pair. All right, so we'll start off by looking at the differential mode small signal analysis of this. We're going to write that the input differential voltage, VID, is equal to VIP minus VIM. The output differential mode voltage is VOP minus VOM. All right, so I can write that the compound transconductance of this amplifier is equal to GMN1, which is equal to GMN2. The output impedance is the impedance that I see looking up, MP2, in parallel with the impedance that I see looking down, MN2. Okay? And this just comes from drawing the half circuit. So the half circuit for this is I have MP2, MN2, and this is my differential input mode voltage. Okay, and so the output impedance that I'm describing here is the impedance that I see looking up in parallel with the impedance that I see looking down. So ROP in parallel with RON. The output voltage that I'm going to get on both sides is going to be equal, but they get different input signs. And so I'm going to get GM times R naught for both sides of this. I have an inversion since this is a common source amplifier. On the positive side, I'm applying my minus voltage, so I have VID divided by 2. On the other side, I have the positive input VIP, and so I'm applying VID over 2. And so what this means is that the differential voltage gain, VOD divided by VID, is simply equal to GM times R naught. On the common mode input, same kind of thing, except for now I'm tying VIP and VIM together. And so I have an input common mode voltage that's going to be VIM plus VIP plus VIM divided by 2. I also have the common mode output voltage, which is again VOP plus VOM divided by 2. The small signal half circuit now is slightly different. Instead of just a common source amplifier, and then here I have the tail resistance, where in order to split this up, I need to make this 2 ROT. Okay, and so the transconductance that I get is this source degenerated transconductance, okay, which is equal to GM divided by 1 plus GM RS, where RS in this case is 2 times ROT. The output impedance is equal to RO times 1 plus GMRS, where the RS in this case is 2 ROT, and that's in parallel with the impedance that I see looking up, which is ROP1. Okay. And so the output voltage gain, the small signal voltage gain, is going to be equal to minus GM times R out times the input common mode. And so when I take the VOC divided by VIC, that is, I add these two together, you'll notice that I get that there's gain, okay, or no gain. So very similar to the previous case here, where if I apply common mode input in an ideal differential mode amplifier without any mismatch, I have no common mode gain. If there is mismatch, you can see how one of these two terms would be slightly different. And then when I do the subtraction or the addition here, they would not fully cancel out. And so we would get a non-zero term for the common mode gain. So in terms of the common mode rejection ratio, the common mode rejection ratio is 20 log 10 of the differential mode gain divided by the common mode gain, which in our case would be infinite in this case. All right, so now that we have analyzed, I would say, the primitive and the most fundamental structures for a single-ended OTA as well as a fully differential OTA, I want to move on to some more advanced structures. What I'm going to do with these is we're going to talk about kind of the architectural high-level trade-offs, and I'm going to leave some of the analysis up to you with the caveat that it would follow the exact same procedure that we did previously. All right, so the first structure that I'll talk about is a telescopic single-ended OTA. Again, single-ended meaning that we're only taking the output from one side, and so we're using a current mirror to actively mirror across the current from the other side. Okay, so this looks a lot like the very first amplifier that we started talking about. The key difference here is that we've added cascode devices. Okay, so we've added both NMOS and PMOS devices that are going to give us larger gain from the structure. So how would we bias these? Biasing these would follow very similar structures that we described previously, where we'd use one of the magic batteries to generate the cascode bias voltages here, VB. Notably, biasing this NMOS cascode requires a little bit of thinking about how to do this. Normally, we would bias things relative to ground, okay? However, here, you'll notice that if the input common mode voltage were to go up, and these particular devices, i.e., let's call this VBN, was biased relative to ground, what you would see is that this node here would go up, but the gate wouldn't, okay? And so what that's going to do, this node does not go up. This node is fixed by VBN at VBN minus VOV minus VT. And so when the common mode voltage here goes up, this tail node goes up, but this voltage, this drain voltage, doesn't change, okay? And so these devices, the input differential pair, they can go out of saturation depending on the common mode voltage, okay? The solution to this is rather straightforward, and after you say it, it's very obvious that instead of biasing this relative to ground, we bias it relative to the tail node, okay? If I bias it relative to the tail node, what that means is that if the input common mode goes up, this tail node goes up, and this magic battery just level shifts off of the tail node, okay? And so typically what that means is that you will sink some current into this device, and that means that we will also need to pull the current out of this tail node in addition to what we would normally have running through both sides of this. So this current that's going to come out of this tail, or this node here, is I tail over 2 plus the bias current, okay? And so usually what you'll see is you'll see another transistor, like in the common mode feedback case down here, in order to pull that bias current through this. Biasing the PMOS is much easier since it's relative to VDD. This node is not changing. This is just the kind of very simple structure that we saw previously. All right, so what else does this telescopic structure do? The biggest downside about the telescopic structure is that, yes, we get more gain. We get more gain because essentially now we have a cascaded structure, okay? And so, I'll end up with quite a bit more gain out of this in the sense that the gain is now going to be proportional to GM times R naught squared, okay, by virtue of higher output impedance, okay. This structure still has the same GM as the previous structure. The GM is going to be equal to this differential pair, so I'll call this M1. But it has a much higher output impedance, okay? The output impedance is the impedance that I see looking up in parallel with the impedance that I see looking down. And in this case, R out is going to be ROP times 1 plus GMP ROP. And this is in parallel with RON times 1 plus GMN RON. Okay, and so this is where we would simplify this to say that this is approximately equal to GM R naught squared. Okay, and then when I multiply it by this other GM, I get GM squared RO squared. Okay, so this is great in terms of gain. It's terrible in terms of its output swing. So in addition to now needing to keep this device in saturation, I also have this device that I have to keep in saturation, as well as this cascode. And so I'm going to add 2 additional VOVs at a minimum, depending on how I implement this biasing network, in order to keep all of this structure in saturation. Okay, so the downside is that I'm going to get very bad output range and a fairly limited input common mode range for similar reasons, that I just don't have a lot of swing from stacking things. This used to be a really, really popular structure when you had 5 volts of VDD or even 15 volts. There was plenty of room to do what's called this telescopic OTA. However, in technologies where you have 1.5 volts, people typically don't do this. Okay. The telescopic name comes from, if you've ever seen one of those folding telescopes that you can pull out and they kind of all stack together. This is kind of that stacked structure. Okay. In terms of the frequency response, we're going to have poles at the output from the capacitance. But in addition to that, we're also going to have poles at these intermediate nodes. Okay, and so these intermediate nodes are going to give us hopefully non-dominant poles, in particular because they see a low impedance. And so we're going to have some additional poles that we have to compensate and keep track of, in addition to that pole zero doublet that still exists from this connection of mirroring the current across this device. All right, so one improvement on this previous structure is what's known as a folded cascode. And so the idea here is that rather than continue to stack these devices, we fold the current into this branch. Okay, and so what the folded cascode does is it takes current and it adds this current into this node. And so if we think about this device up here, we have I tail flowing through this. And down here, I'm pulling I tail over 2. Okay, this device is also pulling I tail, which means that I have I tail over 2 running through each of these branches. Okay, and so this is a nice structure that alleviates some of the output, in particular common mode range problems of the previous circuit that I didn't quite have as much swing. This helps a lot with the input common mode range. And so this circuit is actually a very popular circuit and widely used in a lot of amplifiers. It has behavior that's very similar to the telescopic OTA. in terms of its frequency response, its poles and zeros, we're still going to have some non-dominant poles at each of these cascode nodes. In addition to the dominant pole here at the output, which I'll talk about in just a few seconds. I will say that the biasing is slightly more difficult. For this NMOS device, it's very straightforward to do the biasing because we know that I-tail over 2 is running through both sides of this. This top one is a little bit more interesting in the sense that as I've drawn it here, it's what's called a 1-to-1 ratio of the current that flows through this side versus the current that flows through the load device. Okay. Oftentimes for power reasons, you won't do this. You'll in fact do something like 10-to-1. Okay. And the reason being very simple, the current on this side, this gives me my GM, my transconductance. This branch over here is really just to provide an output impedance. Okay. And so I get benefit from having low current in the output impedance in the output side, and I get benefit in terms of transconductance from having more current on this side. What that does, though, is it makes these two transistors right here, these top two PMOS, a little bit more difficult to bias. Probably the most straightforward way to do this is actually to break them up. And if you think about this as two different devices, one that's feeding this side over here, and one that's feeding this side over here, then it becomes rather straightforward because then you're trying to fit 10 times the current and 1 times the current into this device. You can simply use the M factor or the number of devices in parallel in order to bias this properly. But do think a little bit about the biasing of this. I will say the one bad side or one downside of doing this ratioing is that you often end up with a lot of capacitance at this node. And if you don't have the low impedance from this 1/GM term that we see here, it can start to create a non-dominant pole that falls within your bandwidth. It's not as far out as you would like. All right, so advantages. Common mode can be chosen fairly arbitrarily. It doesn't really affect the signal path in the same way that the telescopic OTA does. One of the disadvantages is that we now have two branches. So I have current that's flowing through this side, as well as current that's flowing through the load side. And so I have additional power consumption. This is usually worth the trade-off of getting back some output swing and having a much wider input common mode range. I also briefly mentioned before about this folding node capacitance. You'll end up with quite a bit of capacitance here, and so it's not uncommon for this to be the limiting non-dominant pole. All right, so another structure, it's a little bit different. These are still what are called single stage OTAs, is a current mirror OTA. And so a current mirror OTA operates off of the principle of having a differential pair. And instead of trying to turn that back into a voltage here, it simply mirrors the current, okay? And so it gets its name that it mirrors the current from this side back into this other branch. And more importantly, it does so with a ratio, okay? It does so with a ratio of M. And so if I think about this input stage as providing me some transconductance, some GM. Remember, these two transistors are the only two transistors in this entire structure, a lot like the previous two, that provide any transconductance. When I copy this current and I copy it and I ratio it by M times, this gives me M times the transconductance. Okay? And so this is nice in the sense that I get to have additional GM, but more importantly, all of these nodes are fairly low impedance. And when I say low impedance, it's because I have this diode connected device, and so the impedance into this node is 1 over GM. Okay? And so even if I have a bunch of capacitance here, it sees a very low impedance, which means that it's going to be a very high frequency non-dominant pole. Okay? This does start to pick up as we scale these devices, because remember that these are going to be M times larger devices. So similar to the folded cascode, I will have capacitance here that can turn into non-dominant poles. Okay. In terms of biasing, this is actually a very straightforward circuit to bias. I just use our conventional magic battery biasing for the cascode nodes. I don't need to even bias these two nodes that I spent a considerable amount of time talking about on the previous slide, since they're current mirrored from this input device and ratioed. The load is very straightforward, and then again, we're going to do a diode connected device here. Very importantly, one of the drawbacks of the previous two amplifiers was that they can suffer from some Miller effect problems. And recall that Miller effect was when we had capacitance between the gate and the drain, and the CGD in a high gain stage, it gets multiplied. Okay, and so I end up with a capacitance at the input and a capacitance at the output that can be appreciably larger than CGD itself. In this particular case, the voltage gain in this first stage is actually quite limited. Okay. And so if we were to write out the voltage gain, the small signal voltage gain of just this input stage, I essentially have GM from these devices minus GM divided by the impedance that I see here, which is 1 over GM, which is equal to 1. Okay. So what that says is that in terms of voltage gain, I actually don't get any voltage gain from this first stage. Okay. I have a low impedance stage that's simply copying the current. Where I do get voltage gain is now this current is being injected into this load, which is simply here to make a large resistance. Okay. So very much like the folded cascode stage, what I'm doing is I'm taking a transconductor, in this case M times GM, and I'm dumping this current into the output impedance of the device, and that's how I'm getting high closed loop gain. Okay, where the output impedance is the impedance that I see looking up here in parallel with the output impedance that I see looking down here. Okay. So this is really useful for applications that are not trying to push process limits. It's very easy to design, very easy to bias, relatively good for low power applications. And so if you're curious about this, Yao is a pretty good reference from back in 2004. All right, so now I want to walk through a couple of examples to show you how you might actually use these OTAs in much larger structures. Okay, and so what I'm showing you here is an analog to digital converter for an audio application. Okay, this is what's called a sigma delta modulator. It's essentially a cascade of integrators and then a comparator back here at the end with feedback around it in order to drive these switches back here at the inputs in order to balance out and stabilize the system. Okay. What you'll notice is that we have several OTAs. In this case, we have 3 of these operational transconductance amplifiers that I was talking about, and you'll notice that there's no resistors. Okay. There are only capacitors and switches. Okay. And so this is what's known as a switched capacitor circuit, and I'll talk about this in just a few slides about how switched capacitors work. The important part here is that the OTAs only ever see high impedance loads, okay? And so we don't have any output resistance or small resistance that loads this output stage. So these switched capacitor circuits are something that you will talk about extensively in 264. They're essentially the way that all integrated circuits are designed. Okay, so let me give you just a little bit of a preview on this idea of switched capacitors and how they work. So if I had a resistor, okay, and this resistor, I'm telling you that we could replace this with a capacitor that we switch, okay? And the idea is that in Phi1, okay, I take this capacitor and I short these two switches, okay? And so essentially what I'm doing is I'm connecting both sides of this capacitor to ground while I open the input and I open the output, okay? So I'm clearing off all of the charge. Then in phase 2, I connect this capacitor between the input and between the output, okay? And these two clocks are what are called non-overlapping, okay? So these non-overlapping clocks mean that only Phi1 or only Phi2 are on at any given time, okay? And so what I want to do is I want to calculate if this was inside of a black box and you didn't tell me that there was a switched capacitor in here, I just wanted to calculate what was inside, what was the impedance. I would essentially measure the voltage across this and use the current in order to calculate the effective impedance. Okay? And so we can work through this. When this capacitor is connected, the charge that I'm going to store on this capacitor is equal to C times the voltage difference between V1 and V2. Okay? And so we're going to call that dQ. The average current that I'm going to pull from this is dQ dt, okay, which is equal to dQ divided by the period of my clock, okay, how frequently I do this, which is F times C times V1 minus V2, which if I use this expression here now to calculate an impedance, I get that the average resistance, not the instantaneous, the average over this entire period is equal to 1 over FC. Okay? And so what this says is that I can use a capacitor, and depending on how quickly I switch this, I can mimic the behavior of a resistor. Okay? And so this is what's known as a switched capacitor resistor. So what can you do with switched capacitor resistors? One, we could build filters, right? So if you think about a conventional RC filter, you would say that an RC filter looks something like this. Okay? I can replace this resistor with a switched capacitor equivalent. Okay? This is the exact same switched capacitor that I showed on the previous slide, and so it should be pretty obvious that we can build this type of filter. We could also build integrators, and so again, normally I would have a resistor coming into my amplifier. Here, I've replaced this structure here with a switched capacitor resistor. And so it functions in very similar fashion. However, it works on the charge domain in order to form this integrator. I could also build a gain stage. And so this is actually what I was showing you very start of this lecture, where we essentially built a amplifier that has a switched capacitor feedback network, as well as a switched capacitor input network. And so now I've built an amplifier that, by combining Phi1 and this switch, during phi1, we essentially connect this capacitor to ground, depleting all the charge. So we set Q is equal to 0. At the same time, we're also disconnecting this capacitor. This other side is set equal to 0. And so both sides of this capacitor are also shorted. Okay? And then when we go into the amplifying stage, now we connect this capacitor and we connect it to the amplifier. Okay, and so this is where we're forming the switched capacitor gain stage. Okay, and so you can kind of see that these are pretty powerful techniques, being that I can use a clock and a capacitor in order to form the equivalent resistance. All right, so here's just a little bit of this circuit again, showing you what's happening specifically during phi2. During phi2, we have the structure that I just drew out, where I have current that's coming in, and then current that's going to be flowing through CF, where we can write that for an ideal amplifier, this current is going to be equal to the input voltage times j omega Cs, where the output is going to be equal to minus I times 1 over j omega Cf, which is that the output divided by the input is equal to minus Cs divided by Cf. Okay, so using a ratio of capacitors, I can set the gain of this switched capacitor amplifier. And so if you recall back from our lecture about PVT and being able to make things that are ratiometric, this is a very powerful thing. It's very hard for me to make an exact, call it 1 pico or 100 femto capacitor, but if I want to make two capacitors that have a ratio of 2 to 1 or 3 to 1 or 4 to 1, that's something that I can do very accurately. Okay? And importantly, we're using capacitors here, so this can be implemented as an OTA rather than having to have an output stage like a classical op-amp. All right, so now we get to the notion of what's called frequency compensation. So frequency compensation is all about managing the frequency response such that when we put this amplifier in feedback, we know where all of the poles and zeros are. Okay, and so oftentimes this is talked about in terms of the stability criteria. Okay, and so there's multiple ways of looking at stability. We'll talk about them in the feedback lecture next time. Two typical ways that one would assess stability are the phase margin and the gain margin. Okay. Coming back to kind of the start of this lecture, we talked about operational amplifiers. In operational amplifiers, you often don't know what the user is going to put for feedback. Some may have resistive loads, some may have resistive and capacitive loads. And so what that means is that in operational amplifiers, you typically only compensate the forward path. Okay, there are some cases where you will do compensation within the feedback network itself, but for the most part, you're going to focus on compensating the feed forward path. Okay, and so there's a couple of different ways. There's many ways. These are 3 ways of doing compensation in practice. Okay, and so I'll go through all of these examples. The first one is called narrowbanding, which is another form of lag compensation. The second one is pole splitting, which is often with Miller compensation or cascode compensation. And then the last one is feed forward, which is a form of lead compensation. All right, so let's start with narrowbanding. The idea of narrowbanding is that we are going to create a low frequency pole in order to ensure that we have sufficient phase margin. Okay? And so let's take this particular example where our open loop amplifier had a response that looks like this. Okay? And so you can see that we have a pole here. We start to lose 20 dB per decade. We hit another pole, and we have a third pole. Okay? We can also see from the phase response that if we hit these poles, and they're all very closely related, you would say that this particular circuit if we were to find the unity gain frequency here, it does not have much phase margin. Okay, in this particular case, it has very, very poor phase margin, in part because we're hitting these three poles all very closely spaced. Okay? And so the alternative is that if we were to introduce a dominant pole, i.e. we were to bring this and put this dominant pole way back here, okay, what we're doing is we're rolling off a lot of the gain before we even get to these non-dominant pole frequencies. And so what that does is that means that when we look at the phase margin here, you can see that we have considerable more phase margin versus this other case where we actually had negative phase margin. So this other original uncompensated case would be unstable. This case, we've stabilized the amplifier by adding load compensation. And so what do I mean by load compensation? Let's take our folded cascode amplifier, and rather than draw this all out, I'm going to simply write that this is a folded cascode. Okay, so I have my differential inputs. The way that I'm going to compensate this is by adding an output capacitance. Okay, so if you recall that in a folded cascode, the input pair is generating my transconductance. I'm going to pick up non-dominant poles from all of the cascode nodes. Okay, and I'm going to have a pole at the output. What I'm doing with this capacitor is I'm adding capacitance in order to bring back in this pole and narrowband the circuit. Okay, narrowbanding simply means that I'm pulling in and I'm creating a dominant pole. This is very common in single stage amplifiers. So almost all single stage amplifiers have what's called load compensation or narrowbanding compensation. All that load compensation says is that we're going to add some amount of capacitance at the output that's going to stabilize the circuit. So if we look a little bit more detail at this folded cascode, I'm showing you kind of the bottom half of the half circuit. There would also be some biasing circuits up here. This could be the folded cascode. This could be the telescopic. All of these have the same kind of small signal structure here with slightly different values for GM and R0. Okay. This capacitor at the cascode node right here, CP, this is giving us a non-dominant pole at fairly high frequencies. And so we're adding enough capacitance CL in order to compensate this via this mechanism of what's load compensation. Okay. As I said previously, this is used in almost all single stage amplifiers in order to get compensation. All right, so what if we had multiple stages? So in particular, what if we had a two-stage amplifier? The idea being that maybe we didn't have quite enough output swing, or we didn't have quite enough gain with any of the structures that I talked about earlier. What if we start cascading them and we make a two-stage amplifier? The two-stage amplifier, shown below, what I'm doing is I'm abstracting this away in the sense that I'm saying that I have a transconductance and I have an output impedance for the first stage, and I have a transconductance and an output impedance for the second stage. Again, this is a pretty common structure where we will have a high gain stage, but with that high gain, we might not get much swing. And so this is meant to be a low to moderate gain, but a wider swing stage such that we get an overall path gain that is the product of these two gains. Okay. All right, so if I was to look at this particular structure, I would find that there are two poles. I have a pole that's being formed from this, and I have a pole that's being formed from this. Okay, and so I have two poles, one at omega p1 at 1 over r1 c1 and omega p2 at 1 over r2 c2. It could be the case that these two poles are actually quite similar in frequency, especially if I implemented this with very similar gain stages. Okay? And so the question is, how would I stabilize an amplifier that does this? It would be extremely power inefficient to try to add cap here in order to bring down the bandwidth. Okay? And so load compensation, I would not say never, but is very, very rarely done in a two-stage amplifier because there's better methods of dealing with this. All right, so this is the first method that we'll talk about. It's called pole splitting. Okay, and so pole splitting, what we're going to do is we're going to take advantage of the Miller effect. So recall that when I had a capacitor, and it's coupled from the input to the output, okay, this capacitor is going to get Miller multiplied. Okay, and so at low frequency, what's going to happen is that there's going to be an additional capacitance here. Okay, and in addition to that, we're also going to get another capacitance at the output. Okay. And we can calculate these capacitances based on the Miller multiplication. Okay. But something very special happens. Okay. When I multiply this capacitor is now going to be CC times K, where K is the gain of this stage. Okay. And so what that did is that brought in this pole. So that made omega P1 is now lower frequency. Now, once this pole occurs, we start to roll off the gain, okay? This capacitance is now shorted out, okay? And so what happens here is that C2, it used to see this impedance of R2, okay? But when CC is shorting out, what is the impedance that I see looking back into the circuit? It's not R2 anymore. It's 1 over GM2 in parallel with R2. Okay? And so what happens is this provides a low impedance path for this. And so what happens is I brought WP1 to lower frequency, and WP2, the impedance is now lower than R2, and so WP2 moved to a higher frequency. And so this is where it gets the name of pole splitting, okay? And I'll show you on the next slide graphically what this looks like. So we would get, if we did KCL, KVL on this, we would get two poles. We would get a pole at the input that is due to CC1 being Miller multiplied by GM2R2, and it's seeing the impedance of R1 at the output. I would get that there's a Miller multiplication of CC, and I also get, I see the impedance of 1 over GM2. Okay, you can actually go through all of the math and you'll see that you do see part of C1 in this expression, and so that's where this C1 term is coming in. Additionally, I also get a 0. For right now, let's not worry about the 0. We'll talk about how we can mitigate and deal with this in just a second. Okay. So what this does is this allows us a very nice way of using CC to reduce WP1 and increase WP2. What this means is this is how I adjust the phase margin of this circuit. If I want more phase margin, I need to push the poles farther apart, which means that I need to increase CC. Okay. This 0, it occurs at relatively high frequencies. You'll notice that it is a right half plane 0, so these are left half plane poles. And I don't really like right half plane zeros. We'll talk about what we can do in just a few minutes to mitigate this, but for just a second, let's focus on P1 and P2. All right, so if I look at the S-plane, originally I had poles right here, omega P1 and omega P2, okay? This is the original pole locations. Now, I add CC, and what happens? This pole moved in to lower frequency. This pole moved out to higher frequency, okay? This is graphically showing us pole splitting. The two poles got farther apart, which increased my phase margin, okay? If the two poles move together and they both move together in, I would not do anything to my phase margin. My phase margin is all about the difference in frequency between these two poles, okay? So it's really important that we're able to position them separately, but even better that we can do one going in and one going out. Okay, so a couple of things that help for simplifications. If C1 times C2 divided by CC is much less than C1 plus C2, okay? This is often the case if you think about this when you're adding CC that is somewhat reasonable in size, okay? Then the second pole simply turns into minus GM2 divided by C1 plus C2. And then the other thing is that if CC times GM2 R2 is much, much greater than C1, that is simply to say that the Miller multiplied version of CC is greater than the capacitance that I already had at that node, that the first pole is then essentially 1 over CC times GM2 R2 R1. We're just taking away this C1 term here. Okay. So this does tell us something. Importantly, in pole splitting, you want to have some gain. You want to have gain in the second stage. So writing this out as AV2, I benefit from one, putting CC there, but I benefit the most when I actually have some gain. And so you'll typically try to get at least 10, 15 dB, if not more, gain in the second stage in order to make this Miller multiplication technique impactful. Otherwise, you would just put CC and load down the first pole. Okay, so now let's come back in and let's talk about this zero. In addition to the two poles that I have, from this and this, okay, I also have a zero. And the zero is because the signal can either come in here and then go back down and back out in kind of its conventional path, or in the case of this CC, signal can come in and it can race forward to the output. Okay, and so this gives us a zero. In this case, it's a right half plane zero at a frequency of GM2 divided by CC. Right half plane zeros are not great. In fact, they're pretty bad for our phase margin. They have a plus 20 dB per decade magnitude response, which is good. That's what we conventionally think of from a zero. However, the phase has a minus 90 degrees phase shift per decade, which is like a pole. Okay, so the gain is going up, the phase is going down. This is really, really bad for phase margin. Okay. All right, so what can we do to mitigate this? One technique is that we can add another element here, and I'm going to call this a nulling resistor, RZ. Okay? And so this nulling resistor, it gives us an additional degree of freedom to position where the zero is. All right, so we got a couple of options. One, I can move the zero to positive infinity. Okay? And I can do that by setting RZ is equal to 1 over GM2. Okay? There are a few assumptions here that we need to make sure are correct, and that's that RZ is much, much less than R1, and RZ is much, much less than R2. In practice, this is almost always the case because it's equal to 1 over GM2. Okay? You'll prove this out on the homework, so I won't spend a whole lot of time dwelling into this. I'm simply going to show you the end result, and that's that we can move this to infinity with 1 over GM2. Additionally, or alternatively, we could also move this 0 from the right half plane back into the left half plane, and we could position it right on top of omega p2. Why would I want to do this? This would be what's called pole zero cancellation. Okay, pole zero cancellation is if I get these two right on top of each other, then I effectively cancel out the effect of the pole. Okay, so if you're thinking about which pole you would want to cancel, you would always cancel the lowest frequency pole. Okay, because that's the one that's going to affect your phase margin the most. However, the risk here is that you end up with a very nasty pole zero doublet. Okay, and this doublet is exactly what I started off describing. If you miscalculate or you're not quite right on getting this pole, or excuse me, the 0 position properly, you can miss canceling the 0, and then you can end up with very, very long settling time. Okay, and so, you know, I'm drawing this resistor here as RZ, but more often than not, it's actually going to be implemented as a transistor. Okay, and the reason being is very straightforward, especially in the case of moving it to positive infinity. If I want this to track this device, I should really implement this as a transistor as well. And so then it will track process voltage and temperature variation. Okay. I will say that putting the 0 at positive infinity is a very safe approach. There's really nothing that can go wrong here. You're gonna give up a little bit in terms of your potential phase margin, but it's very, very safe. If RZ was to change by 10, 20%, it would not have a dramatic impact on the frequency stability of the circuit. On the other hand, canceling out this pole, it will give you more phase margin, so it is in theory a much lower power technique. However, if the pole moves by 10, 20%, or excuse me, the 0, you can end up with very bad settling response. So you have to be very careful with this pole 0 cancellation. There's other ways of mitigating this to a degree. I'm showing only a couple here. One is that you could make this feedback path unilateral. So the problem with the 0 is that the signal, we need CC to be here for this path. Okay, we actually don't want it to be there for the feed forward path. And so right now, capacitors and passives in general are bilateral. They allow signals to go in either direction. Okay. One way of making this unilateral is to have this capacitor CC connected to a voltage buffer and now there's no way that signal flows like this. Okay, signal can only flow in the path that we wanted. That is, that it can only flow this direction. Okay, and so this is what we're calling making the feedback path unilateral to mitigate the 0. That will actually cancel out this 0. It does have the complication that I now need to make this buffer, and I need to make this buffer fairly low power. You can do this with a source follower, and it's a pretty common technique as well. All right, so to quickly summarize, if I have a two-stage amplifier and I make the assumption that I'm using a nulling resistor to move the 0 to positive infinity, okay, I could write that the overall gain is the product of the gain from the first stage, AV1, times the gain from the second stage, AV2, okay, which is GM1R1 times GM2R2. The poles that I have in the circuit, pole at the input due to the Miller multiplication of CC, pole at the output due to diode connection of CC. the unity gain frequency, or the gain bandwidth of this amplifier, is omega P1 divided by AV. Okay, so I'm assuming that this is the I'm making this the dominant pole. This is going to be the non-dominant pole. I'll get that the crossover frequency, or the unity gain bandwidth, is equal to GM1 divided by CC. And the phase margin is going to be 90 degrees minus the arctangent of omega C divided by omega P2. Okay. So these are really useful equations that you will likely need for your project. Your project is a little bit more complicated in the sense that R1 is not simply a resistor, it's a more complicated stage, as well as R2. Okay, but these are great summary expressions, and you'll need to derive them out for your particular architecture. All right, so the previous slide we talked about Miller compensation for two-stage amplifier. What if we extend that further to multi-stage amplifiers? Shown here is an example of what's called nested Miller compensation for a three-stage amplifier. So we have three gain stages, GM0, GM1, GM2, with the original frequency response shown down here. We use CM1, which is this first Miller compensation, in order to introduce a pole and push out these two poles. And then we use CM2 in order to come in and introduce an additional pole and further split across these poles for frequency stability. So this is a pretty common technique when you need a lot of gain, or your technology itself does not have a lot of intrinsic gain. And so, think about an amplifier building, for example, 90 dB. It may not be possible in an advanced technology node to get 90 dB from just a single stage or a two-stage amplifier, which would necessitate adding this third gain stage and then compensating it using nested Miller compensation. All right, and one more technique, the last technique that I'll talk about in this lecture, is known as feed-forward compensation. Feed-forward compensation says that I have a transconductance with some output impedance, resistance, and capacitance, a second transconductor, output impedance, output capacitance, and I have an alternative path through this GM3 that feeds forward the signal to the output. And so I have two paths, one for low frequency with a lot of gain that has both of these transconductors, and a second lower frequency path that goes through GM3 that lets high frequency signal get to the output for phase response. This will introduce a zero in the circuit from this alternative path to the output, and we're essentially using this in order to stabilize the circuit. This can make it rather difficult to get good frequency response out of the circuit, but is often needed if you need lots of gain, and especially in newer technology nodes where gain is very hard to come by. All right, so to summarize this lecture, OTAs are very often used in integrated circuits. They're similar in function to an operational amplifier, but much less general purpose, and they only drive capacitive loads. We talked a lot about fully differential amplifiers and why they require a common mode feedback network in order to set the DC output voltage. And then we went through several different architectures for building OTAs: telescopic, folded cascode, current mirror. There's a lot of other architectures as well as hybrids of these where we will cascade multiple stages in order to get a compound amplifier. And then lastly, we spent a little bit of time talking about compensation and managing the poles and zeros for closed loop amplifiers. Thank you.